Good morning. My name is Elijah Rivera. I'm a PhD candidate under Shriram Krishnamurthi at Brown, and I'm here to present our experience with different kinds of composition of higher order functions. This experience report was born out of a separate research project seeking to understand how well students understand compositions of higher order functions in general. As part of this other project, I was tasked with creating new problems for the beginning of Shriram's accelerated intro course at Brown. The problems needed to be solvable with the standard higher order functions on lists, and needed to be of an appropriate difficulty. This proved to be a much more challenging task than expected. I could propose a number of problems, but all of them appeared to be on the two extremes of the difficulty spectrum. I had the ability to generate problems that looked to be trivially easy, or problems that seemed to be much too complex for even an accelerated intro, but nothing in between in this sweet spot. But what really frustrated me is the fact that I couldn't explain to anyone why this was true, or even the difference between the two collections of problems. Why were the challenging problems challenging? And neither could Shriram. After staring at these problems for months, I came up with a hypothesis to explain what exactly makes some of these problems significantly more challenging. Over the course of this talk, I'll present you with the hypothesis, some evidence from a preliminary experiment, and how and why we're seeking to expand this experiment even further. Before I get started, to briefly situate this work, we are currently restricting ourselves to higher order functions on lists, specifically higher order functions with the type signature on screen. These were the types of higher order functions that we were working with in Shriram's course, which is why we use them. Students were in fact restricted to a small subset of these higher order functions, which were presented in the course. Pop quiz. Consider the two following ways of composing higher order functions. I'll give you a moment to read over them. Now, which of these would you consider easier for students to understand and to use? And which of these represents a larger set of possible programs? Really stop and think. I'll give you some more time. If you're watching this video on your own, pause and really think it through. This is vital to the rest of our story. What does your gut say? Before we go further, I'm going to give these different kinds of composition names. I will call composition A pipeline and composition B structural. Let's take a look at why, starting with structural. Let's just do a bit of type analysis on this example that we have. We'll wrap that example in a function called example_fun, which takes in a list of A and produces some type B. Of course, that means that L must have that same type, a list of A. We also said that we're focusing on list higher order functions. So we know that HOFC will take in a function and a list and will output something. And in fact, since it takes in L, it must take in a list of A, meaning that its funarg must take in an element of type A. That element is named inner here, so we can fill in those lines as well. We can also say that HOFC must output the same type as example_fun, so let's fill that in. HOFD is also one of our list higher order functions, so let's put that shape in here as well. Similar to before, we can constrain the types based on the output argument, which here must be the same as the funarg for HOFC, so let's do that. We can also constrain the types based on the input argument, which is inner and has type A. Now I would love to put that straight in, but then I lose the fact that this must be a list. So instead we do some substitution. We'll first say that this higher order function takes a list of type X, and then we'll replace all instances of A with list of X. It's a jarring change at first, but notice what happened. L is now constrained to not only be a list, but a list of lists. Said another way, this composition only works if the type of input list, L, was a doubly nested list. And a similar argument works for any number of higher order functions composed together in this way. I can only nest higher order functions in structural composition up to the depth of my input list. I cannot have 3 of these nestings if my input list is only 2-dimensional. The type constraints simply don't work out. This is why we call it structural composition. The composition must mirror the structure of the input data. This in turn means that when given a finite list of higher order functions, which students were, then for any given input list dimensionality, there are only a finite number of ways that I can structurally compose the allowed higher order functions to operate on that list, because the list higher order functions impose dimensionality constraints on their funargs, and any other higher order functions nested inside must respect those constraints. Now, of course, I can fill in this funarg at the bottom with one of any number of functions matching this type signature, and so that question about the set of possible solutions is a bit misleading. But still, there is a significant constraint imposed on the space, and synthesizers or students exploring the space, searching for solutions, should have a relatively easy time. But easy relative to what? Let's do the same type analysis for the pipeline. Example fun once again takes in a list of A and outputs B, which once again means that L has type list of A. HOFA must still have the type signature of a list higher order function and must still output the final result of type B. HOFB must also be a list higher order function, and it must take in L, which is a list of A. This A then constrains the input type of its funarg. Now we know that HOFA takes as input the output of HOFB, so these two circles must be equivalent. We'll call that a list of X. And that means that the funarg for HOFA must take in an X. And we're done. And in this, we see the key distinction between these two types of compositions. I am no longer constrained by my input type in the same way I was in structural composition. I can, in fact, keep chaining pipeline composition indefinitely, similar to the piping operator in Unix or other similar data processing pipelines, hence the name, as long as I continue to line up the output type of one to the input of the next. This means that that student as a synthesizer is likely going to have a more difficult time, as the solution they are looking for can have unbounded size and looser type constraints. These intermediate list of X types can be anything, as long as the next step in the pipeline accepts that same type of thing. Does this difficulty match your intuition? It certainly didn't match Shriram's when we started, and it went against the intuition of many other experts we spoke to. But it does line up with the experiences we spoke about earlier. In almost all of the examples of this gap I mentioned earlier, the easy problems were structural in nature, and the more difficult problems were pipelines. Observing this apparent distinction in the wild, we set about creating a more controlled instrument, a course assignment that would test my hypothesis that students have more difficulty with pipeline composition than with structural composition. So what's in an assignment? Well, for any assignment, a student takes in a problem statement as input and produces a solution as output. So to design our assignment, we need to both pay attention to problem statements and to solution structure. Let's start by looking at the latter of those two. There are a lot of challenges involved in writing full working code, and not all of those challenges are germane to our question about composition. So instead of asking students to write code for this assignment, we gave them a prompt for text in hopes of seeing their high-level planning structure. The full text of this assignment can be found in the paper, but the instructions are roughly summarized here. You may have noticed that the instructions mentioned a box with examples. We will come back to that in just a moment as we talk about how to present problem statements, the other piece of this puzzle. Here's one standard example of a problem statement. Given a list of numbers, output the same list of numbers, but with the number 5 removed from each inner list. The issue is that most people who have even had some experience with higher order functions will quickly realize certain patterns. Like, removed probably means I need to filter. From each probably indicates a map, and we're basically already done. It's a map of a filter. What's even left? We've given away the problem in the statement. We weren't satisfied with this, so we tried alternatives. Specifically, we took inspiration from a previous education paper on higher order functions, which used input-output pairs as the problem statement. Here's what this looks like for the previous problem. The assignment gives them problem statements that look like examples, like this, and asks them to generalize to those plain text solutions or explain why that is difficult or impossible. Our students had in fact completed this task from the previous paper that we mentioned before starting our task, so they were already familiar with this input-output pair format. With both our problem statement and our solution formats decided, and with hypothesis in mind, we set about our experiment. Students were given 7 problems total, 3 each with structural and pipeline-only solutions, and 1 impossible problem. The problems were presented in a random order, except the first problem, which was always fixed to avoid giving the impossible problem first. So how did they do? The detailed numeric results are in the paper, but they're summarized here in the chart. We see that nearly all students correctly identified the structural composition questions, and less than 75% of them correctly identified the pipeline composition questions. There's also a high degree of uncertainty, represented by the yellow IDK portions of these bars. And this is reflected further in the written text results. More students had the correct answer for the correct reason on the structural problems than on the pipeline problems. There's a more detailed breakdown of the written responses in the paper. We know that this isn't perfect. There are valid challenges to our choice of representation, and this is a small sample at one university. Our goal with this work is not to claim a definitive answer, but to be a starting point, to inspire this community to investigate this phenomenon further. To that end, we are currently actively coordinating a follow-up study to this work across multiple institutions in multiple nations, working in different programming languages. If this work seems interesting, and you or someone you know might like to come on board, please reach out. You can find a detailed write-up of our current research plan at the tiny URL on screen. You are also welcome to reach out to me personally, either via email or on Twitter. We've observed an interesting distinction between different ways of composing higher order functions, and a perceived difficulty gap between them. We've given the names structural and pipeline to these two kinds of composition, and we've provided a small sample of evidence suggesting that students do actually struggle more with pipeline composition than with structural. We are coordinating a follow-up study, and I look forward to hearing from you and answering any questions you may have. Thank you.